Okay, welcome back to linear algebra. In this second short video lecture for section 6.3, we're going to look at some properties of the operator we defined in the previous lecture, the adjoint of T. All right, so let's recall that if you have a finite dimensional inner product space and you take a linear operator on it, its adjoint, T star, is the unique linear operator on V that satisfies that equation. That the inner product of T of x with y is the inner product of x with T star of y for all x and y in V. There's one and only one linear operator on V that satisfies that for all x, y. That linear operator is called the adjoint of T. One of our motivations is we wanted to construct a linear operator whose matrix in an orthonormal basis was the adjoint matrix for the matrix of T. And our first theorem says that we have achieved that goal. So we'll take an inner product space V, it's finite dimensional. We're going to take a linear operator T on it, okay? And let beta be an orthonormal basis. And this equation exactly says that the matrix of the operator T star in the basis beta is the adjoint of the matrix of the operator T in the basis beta. Okay, so when you move that star out, make sure you understand what that equation is saying. It's saying that the adjoint of a certain matrix is the matrix of the adjoint operator. So we have an adjoint operator, we've got an adjoint matrix, and this theorem is relating them. Okay, so to prove it, let's let beta denote our basis, orthonormal basis for our vector space, our inner product space V. And for shorthand, let's let the matrix of T in that beta basis be called A, and the matrix for the adjoint operator be called B. Okay, so basically what I'd like to show is that B is equal to A star. Yeah, that's our goal. I want to show that B is equal to A star. So we're going to find the matrix for B. So when you're finding a matrix for a linear operator, remember that you take the image of any basis vector. So I'm going to take T of Vj, and then I basically want to know what's the coefficient of the ith basis vector. That is, I want to know what is in row I of column J of this matrix B. Well, theorem 6.5 applied to this operator T star says I should take the vector T star of Vj, take its inner product with the basis vector Vi, right? So that's by definition, that's the element in the ith row and jth column of the matrix for T star in the beta basis. But by the adjoint property, I can move T across that comma. I get that that's the inner product of Vj with T of Vi, which by inner product properties, I can flip. That's the conjugate of the inner product of T of Vi with Vj. Well, that's exactly the conjugate of the entry in the ith column of and the jth row of the matrix A, because I'm taking T of Vi, right? So that's why it's the ith column, and I'm looking at the inner product of it with Vj. That's why I'm looking at the jth row, but the complex conjugate is over the thing. But the complex conjugates, if we switch I and j, that's exactly the element in the ij position of A star by definition. All right. So Bij, the ij entry of B, is exactly the ij entry of A star for any I and j. So B is equal to A star, and that's what we were trying to prove in this theorem. Nice. Little corollary to that. Again, make sure you kind of read these things out loud. Don't just look at it as moving some stars around. But this says that the linear transformation that is left multiplication by the adjoint matrix A star is the operator adjoint of the linear operator left multiplication by A. Okay, so how to prove that? If we take the standard orthonormal basis for Fn, then the matrix of the left multiplication operator by A is just A. And likewise, the matrix, the left multiplication operator by A star, the adjoint matrix is just A star. Okay, but by the theorem that we just proved above, the adjoint operator of left multiplication by A, its matrix in this orthonormal basis is the adjoint matrix of the operator of the matrix L sub A in that basis, right? But that's just A star, right? Because the matrix of L sub A in the sigma basis is A. So the adjoint matrix is A star, but we've written above that the A star is the matrix and the sigma basis of the linear operator left multiplication by A star. So if the two matrices in this orthonormal basis are the same, then the linear operators are the same. Nice. So this nice compatibility between this notion of adjoint operator and adjoint matrix. Just as a quick example to illustrate that, if you wanted to say find an adjoint operator formula, if we take, say, a map on C2 defined by that formula, I won't read it out loud, but that's how T operates. And let's say I wanted to find a formula for T star. Okay, well, what would I do? I would just say take the matrix for T in the standard basis. It's written here, and then take the complex conjugate transpose of that matrix. Stop the video and check the details, right? So the theorem, the corollary that we just proved says that that A star adjoint matrix is the matrix of T star in the standard norm in the basis. So if we just use that matrix to write the formula for T star, you get the following formula. So you can use that to produce the adjoint operator. Nice. Okay, so we're going to end here with a couple of theorems that show that there's a really strong analogy between the adjoint of an operator and the conjugate of a complex number. So namely, I'm not going to prove all parts of this theorem 6.11, but each one of these things, if you kind of replaced T and U with complex numbers and the star with the conjugate, the analogous formula holds. So for example, the adjoint of a sum is the sum of the adjoints. The adjoint of a scalar multiple is the complex conjugate scalar multiple of the adjoint. The adjoint of a composition is the composition of the adjoints in the opposite order. The adjoint of the adjoint is the operator, and the adjoint of the identity map is itself. So I'm going to prove a couple of these. The book proves a couple of them, and then you can pick up the pieces. Each case, we're going to make heavy use of that theorem 6.1e, right? So I want to show equality in an inner product space. A common technique to do it is show that if you inner product against an arbitrary vector, you get the same thing. Okay, so I'm going to prove part B. I want to prove that the adjoint of a scalar multiple of T is the scalar's conjugate times the adjoint of T. So I take a couple of vectors X and Y in my vector space and a scalar. And then I look at the inner product of X with CT's adjoint applied to Y. Bring the adjoint across the comma, so it gets rid of the star, and then by the scalar multiple property in the first coordinate of inner product, that C can come out, and then I put the adjoint over back across the comma. Okay, and then I put the scalar multiple back in the second coordinate, but when you do that, you get a conjugate bar on it. Right? So again, by theorem 6.1e, if this is true for all x, then the elements of the second coordinates have to be the same. So that shows by that theorem 6.1e that ct star applied to y is c bar times t star applied to y for every y, and therefore those functions are equal. All right, I'm also going to prove part C. Let's look at it real quick here, that TU star is U star T star. So I'm going to do it the same exact way. I'm going to pick a couple of vectors and I'm going to look at the inner product of TU star of X with TU star applied to Y. Bring the function across the comma, ditches the star. Then I apply TU of X by definition is T of U of X, inner product with Y. Then bring the T across, puts the star over there. Then bring the U across, puts the star over there. And that by definition is U star composed with T star of Y. And once again, by theorem 6.1e, since this is true for every X, the elements in the second coordinates have to be the same. All right. So I'm going to leave this to you to do the details, but if you combine that theorem with the theorem about the fact that how do I say this? I got to slow down. My tongue is dripping here. The adjoint of the linear operator left multiplication by A is left multiplication by the adjoint matrix of A. You combine that with theorem 611 that we just proved a couple of parts of, and you'll get the following corollary that's for matrices. All right. You could prove this corollary directly just using that fundamental identity that if you want to know the ij entry of A star, you just look at the ji entries complex of A. You could use that idea to prove all of these things directly, but you can also use it with theorem 611 above, right? And the fact that left multiplication by the matrices behaves well with conjugate. Okay, thanks for listening.